Okay, good. Screen. Okay. The second part هلا we'll start with the simplified or simplifying conditions, initial and boundary conditions. Simplifying conditions عملناها. Okay, after each paragraph we put the simplified conditions. Then we'll start with the initial and boundary conditions, the variable change, and then the dimensionless numbers, dimensionless equations, and one application concerning this dimensionless number. Okay. So today I think we will finish the first chapter. Okay, and next week we'll treat the finite difference scheme. Now, with the initial and boundary condition, you see this picture?
Yeah.
Yes.
You see this? Okay. Here is a two-dimensional scale. Two-dimensional scale. That's meaning I'm working in two dimensions, x and y. X, the index of x is I. The index of y is j. The index of time is n. Then, if I need to discrete my system in order to the computer to understand the equations and to solve the equation, then I need to create nodes. Look here, there is a node. Here, there is a node. Another node. Another node. Here, a node is characterized by the indexes I and j. Then the position of this node is ij. Then I can write here, if it's the temperature, then I can put Tij. Here is Ti plus 1, because if here is I minus 1, here is I, here I plus 1. Here is J minus 1, J plus 1. Of course, the axes are very long. And here is a small example, a simplified example, because the axis is going from 0 to I max and from 0 to J max. Then I can say here 0, 3 points, 3 points, I max. 0, 3 points, 3 points, J max. That's meaning we have several horizontal lines and several vertical lines, but I cannot show all the lines here in this picture. Then the position I, J is here. The position I plus 1 J, I minus 1 J, position IJ plus minus 1, IJ plus 1. Hala. If I need to say to give you the initial conditions, what does mean the initial condition? يعني أنا بفوت على الغرفة، إذا عندكم بلاط بالصالون تبعكم أو بالغرفة اللي أنتم فيها، تطلعوا بالبلاط. Okay. 2 dimension هو هالروم هي has perpendicular shape or rectangular shape. Okay. بس عم تطلعوا بالبلاط، البلاط شو؟ has horizontal lines and vertical lines, and there are nodes. عم تشوفون عندكم يلي عنده بلاط ما عنده باركيه؟
يب.
معي على السما؟
نحن معك.
اوكي. تطلعوا بالبلاط عندكم بتشوفوا في nodes. The initial condition and when the all nodes at initial time has known values. يعني معروفين. At initial time في يكون t equal 0 second وفي يكون t equal t0 whatever t0. أنا بحدد حيلا t0 وبقلع منها. الكالكوليشن. مفهوم؟
مفهوم.
اوكي. لكن the initial condition is a long time. It is the initial time. Boundary conditions is along or in concerning the borders of the space, x space and y space, the borders. Okay, هي اللي عليها بالborders. When x equals 0 or x max, when y equals 0 or y equal y max. مفهوم؟ هيدي الباوندري كونديشن. اما الانيشال كونديشن is in relation with time. يعني initial condition all the node here كلها النودز هون كلهم بده يكونوا معروفين. good. خلينا نبلش بالباوندري كونديشنز وبعدين برجع بشوف. boundary condition when x equal 0, this is this points here, whatever y, all these points is for x equals 0, whatever y. يعني I equals 0, j is going from 1 to n or to j max. Okay, أنا حاطط thermocouples on, there are thermocouples on, then I can measure the temperature. And then these points or these nodes are known values. For I equal I max, that's meaning x equal x max, all these nodes here, whatever y, are known, معروفين, and I put thermocouples here, and they can give me the value of the temperature a long time. شو ما يكون الوقت أنا عم يعطيني time هون. هالتايم نحن بنقطعه per step, and I can say each 10 seconds, each 1 second, each 1 microsecond, you give me an answer. Okay, like each 10 seconds I have an answer. Then we have values here at these points here, whatever the time, okay, along the time. هيدي for x equals 0, x max. How the boundary condition على x? The boundary condition على y, when y equals 0, then these values here are known values, and I put thermocouples here. Okay, and if y equal y max, all these values are known values. Okay, then all the boundary values or the boundary values here having known values. Then from these values, from these 3 points, this one, and this one, I can calculate this one. From these 3 points, I can calculate this one. From these 3 points, I can calculate this one. And the following, in order to calculate all the points inside the grid. Okay? And then I find all the values at time t equal 1. Okay? And then I repeat the calculation for time equal 2 and for time equal 3 and the following. Okay? هيك بتصير الأمور. Good. I start with the initial condition when t belong t0, then we'll say the index n here is equal to 0. Index n here is equal to 0. For the temperature, velocity, and mass fraction. Okay? And then all the values here at time t below to 0 are known values. كلهم سوا. مفهوم؟
ديل.
كلهم معروفين at time t equals 0. But at time t bigger than t0, we don't know. Okay, we need to calculate all these values. مفهوم؟
مفهوم.
Now, for the boundary condition, when t is bigger than t0, only that I know is t equal to 1 for I equals 0. يعني هيدي. Here we have 300 Kelvin. Okay, and for Imax is here, Imax. Here We have adiabatic. This one is adiabatic. Heat source. Here is a constant value which is called Dirichlet. Dirichlet condition. Here is called the Newman condition. Newman condition. Here is a condition. What does mean dt over dx? Dt over dx, that's mean t I plus 1 j n is equal to ti j n. تي اي جي ان اي ماينس 1 يعني هيدي بتساوي هيدي، هيدي بتساوي هيدي، هيدي بتساوي هيدي، ادياباتيك، هيدي بتساوي هيدي، هيدي بتساوي هيدي. And if I calculate this one, then this one is known value, is calculated. Adiabatic. Along y, if I put here t equals 600, t equals 600 Kelvin, where here we have 600 Kelvin. But up, we have dt over dy equals 0 for here, adiabatic values. Why? Because ti j plus 1 n is equal ti j n. ti j n. j plus 1 بتساوي j لأنه adiabatic. Okay, then from this known value I can determine the remaining points. مفهوم؟
Okay.
Hidden initial boundary conditions. Now I can put also heat flux. I can put also Newton condition. Newton condition is when I put H delta T, convection. Okay, convection. I can put a conduction application in lambda, continuity of the conduction, in lambda 1 dt over dy equal lambda 2 dt over dy. We have several kind of conditions that I can put, okay, in order to complete our model and to solve the equation. Okay?
Till.
You see that in your book here, in your manuscript, and you find there are several examples concerning that. Now for the variable change, to simplify our writing of the mathematical equation, one can pass from a coordinate to another one, and the easiest coordinate, which is the easiest coordinate? Maybe which is the easiest coordinate? The Cartesian coordinate. Cartesian coordinate he is the easiest one. Then we need to pass from the cylindrical and spherical coordinate to Cartesian coordinate. And sometime we need to linearize our equation to linear, as this example here, because I have spherical form. Sphere, we have a sphere. Then we have a spherical coordinate. In order to pass from sphere to line, I need to do like this kind of variable change. TR is d eta r plus r over rs, which is 1. Here is rs, here is 1. And here is theta. Or t, whatever, or t or theta, what, depending on the variables. Mafhum? It is an example. Then I pass directly to the dimensionless numbers and equations. Dimensionless numbers. The dimensionless number or dimensionless equation is used to write the partial differential equation in general forms by eliminating all the units and by appearing the dimensionless numbers. مفهوم؟
منيح.
واضح؟ انا ما بقعد عندي يونتس، بصير عندي شو؟ بدل ما يكون عندي رو لوحده، السي بي لوحده، الفيسكوزيتي، الدنسيتي، الديفيوزيفيتي لوحدهم. انا I put all these parameters together in dimensionless numbers, such as Reynolds number here, rho VD over mu, rho density V velocity D is a characteristic مثل هيدا نهر عنده D distance D اوكي وعنده velocity V max on V V max على البوردرز تبع النهر بيكون زيرو على طول ما في عندنا ستريمينج على البوردرز بيكون زيرو بنص النهر بيكون في ماكس اذا بدكم تكبوا حدا ويشعلوا وياخذوا النهر تحملوه بتكبوا بنص النهر بتكون سرعه النهر اقوى من طرفه الطرف بتكون سرعه اخف مفهوم؟ like rho d over mu Reynolds شو بيقول لنا؟ the water is if it is below 2000 we have laminar streaming if Reynolds is greater than 2000 we have turbulent streaming turbulent flow laminar flow or turbulent flow for the water 2000 for another kind of liquid the number is different for Reynolds مفهوم؟
Okay.
فهمتوا شو هو Reynolds؟
Yes.
The Graham number, that's my number. The Graham number is rotating if we have a rotational flow. Rotational flow. Flow رايح rotational. عم يبرم. Then we compare the frequency of rotation over the viscosity of the fluid, which is the preponderant, which is the bigger, which is the greater. Okay, the rotation or the viscosity. مفهوم? And it can be used in several applications such as tornado, twister, and in several systems where the fluid, the viscous fluid is in rotation. مفهوم? And in all equations now, in my equation and other equation, we can find Reynolds over Graham also. This one is for the linear streaming, and this one if we have rotational, because Reynolds is for the old مثل كان نحكي نيوتن وهذا نيوتن عطى classical نيوتن عطى classic mechanics يعني هالميكانكس بتروح من هون لهون لهالشقفه لانه as نيوتن formulas بعد منها شو اجى سيستم ثاني بكفي نيوتن يلي هو شو الفورمولا تبع اينشتاين وتبع الفورمولا ريلاتيفيتي اوكي بتكفي نيوتن بس نيوتن is true بس it's true till this condition after this condition we need to use a formula of Einstein formula relativity and restraint and complete relativity formula. Also here if we are working in some system without rotation we need to use Reynolds. If the rotation is coming then we need to add the Graham number. I published this in 5 publications. Okay, منشورين 5 publications where there is a link between Reynolds and the Graham. Also, Nusselt number is the convection over the conduction, which is the dominant here. Is a convection or the conduction. Okay, we need here give us information about the transfer mode. We have Sherwood for the mass transfer, Schmidt for the mass transfer, Prandtl for the heat transfer also, and we have Beckley number, we have Grashof number for the natural convection, we have Rayleigh number, which is Grashof Prandtl thermal Rayleigh number, and Grashof Schmidt for the mass Rayleigh number. Okay?
Deal.
Good. They are non-dimensional numbers that quantify between two forces or between two phenomena. They are used to simplify the explanation of all phenomena. The dimensionless numbers such as Fourier, Biot, yani, Nusselt, Sherwood, Prandtl, Schmidt, Reynolds, Graham, etc. They are used to simplify the equations. Then we need to start. بدكم تحطوا ورقة وقلم إذا بتريدوا. بتبلشوا لي شغل. يلا هيدي الايكويشن. I give you this equation. Does this equation is true? Describe the above equation. Give the whole simplified conditions. Make this equation dimensionless. يلا معكم بعطيكم ربع ساعة لألا اشتغلوا. اوكي نرجع نصلحها سوا. بلشنا هيك بالاكزام بيصير. هيك بيجي بالاكزام. اوكي
Yeah.
اوكي يلا بس تا حط ميوت.